So you just have to regurgitate what I did in class and split them up in the homework. So I hope it's not too difficult. That's good.
I'm slightly confused on how to prove uniqueness for Poisson equation.
How to prove uniqueness of Poisson's equation?
Because the derivation given in textbook, we consider if the imaginary part of k square is not equal to 0, but in Poisson's equation that's not equal to 0. So how do I go about that?
Well, you can use the same approach, I suppose. I don't know, I never proved it before, but I would think that we try to prove that. So you have the same source. Okay, you claim that this source gives you two different solutions and you subtract. You have the phi must be equal to phi1 minus phi2. And then you do integration by parts. And the most natural thing will be to multiply this equation by delta phi. Let's assume that delta phi is a real number so that we don't have to do complex quantification. And then you do integration by parts, and hopefully that you will get something like dv delta phi dot delta phi is equal to 0, which is delta phi. And then you impose the boundary condition so that the boundary terms go to 0 when you do integration by parts, and you can argue that this is a positive definite number. And the only way for this positive number to be 0 is for this to be 0 everywhere. And hence, we put uniqueness this way. Right.
If that's 0, then delta phi can be a constant.
Or delta phi can be a constant, of course. Poisson's equation is actually not unique in the sense that it satisfies the equation up to an arbitrary constant. Right? You solve Poisson's equation, you solve Laplace equation, you can always add a constant to those equations and get them satisfied. And I believe that's what you're seeing here, right? You can add a constant to this, but if you add a constant, then the boundary condition might not be satisfied, depending on whether you have a Neumann or Dirichlet boundary condition, and those boundary terms might not vanish. But assuming that those boundary terms vanish when you do the integration by parts, you go from here to here, the proof should go through. Okay, so this implies delta phi, at least the gradient of delta phi must be 0, that's what it says. That's what it means, right? So you solve to within an arbitrary constant, I suppose. You can have this solution, you add a constant, you can have that solution, you add a constant, and then it should vanish, that's what it says. Okay? But I never did it before, so I don't know. Okay? So let's go back to reflection by layered medium. And we did this very simple case last time. We have medium 1, medium 2, medium 3, and then we wrote down the solutions for each region. Like in region 1, we wrote down the solution as something like, let me see what I wrote down. A1 e to the minus I k1 z plus a reflection term R12 tilde into the I k1 z plus 2 I k K1Z D. Okay, we wrote down the solution. In region 1, this is B1, C equals minus D1, C equals minus D2. Okay. And then we wrote down solution for region 2 is A2 e to the minus I K2Z Z plus R23 e to the I K2Z Z plus 2I K2Z D2. And then we wrote down solution for region 3, that's been A3 e to the minus I K3Z Z. So we have upgoing wave and downgoing wave in this region, we have both of this region, and in the third region we only have downgoing wave. That was what the motivation for the solutions are. And then we have to be careful that these are all K1Z, K2Z, and K3Z. They're all different in different regions, but they all share the same Kx. Due to the phase matching condition, all the Kx's have to be the same. Okay. But all the Kz's will be different in all the three regions. And then we add in constraint conditions. Not boundary conditions, constraint conditions. From the Fresnel reflection and transmission coefficient, then we got the fact that R12 tilde must be something like R12 plus P12 R23 P21 e to the 2I K2Z D2 minus D1. Okay, D2 minus D1 is this thickness over here. Okay, and then divided by this number, 1 minus R21 R23 e to the 2I K1Z D2 minus D1. Okay, we went through the exercise and we don't need to go through that again. And actually, you can write this in a simpler form if you want to, knowing the fact that 1 plus Tij is to the Rij. This is something which is true for the Fresnel reflection coefficient. And hence I can write T12 as 1 plus R12. And then I can also realize that R12 is equal to minus R21. You look at the definition for the Fresnel reflection coefficient and realize that this is in fact true. So T21 is 1 plus R12 times 1 minus R12. This was previously 1 plus R21, but it became 1 minus R21, and hence you can write that as 1 minus R12 squared. Okay, and if you plug that in and multiply things out, then you will find that if you multiply this thing out and bring everything on the common denominator, then if you make use of this factor over here, you will have R23 e to the 2I K1Z D2 minus D1 as the term that comes with 1, and then multiply by R23, and then you will have something like let me see if I got things correctly. And then there will be one remaining term coming from here. Okay, that remaining term will be R23 R12 squared e to the 2 something. And then there will be one more remaining term coming from this, multiplied by that. Okay, that would be something like plus R23 R12 squared e to the 2 something. And then everything can be brought under the same denominator, R23 R23 e to the 2I K. This should be 2Z, sorry, this should be 2Z, K2Z D2 minus D1. Okay, you can show that these two terms cancel each other because they are of the opposite sign. Okay, so this reflection coefficient, which is called a generalized reflection coefficient. Okay. Can also be written in a simplified form, R12 plus R23. This should be 2, I'm sorry. 2. E to the K2Z B2 minus B1 over the denominator, which is 1 minus R21 R23 e to the 2I K2Z B2 minus B1. Okay? So this is the generalized reflection coefficient that we find for R12 tilde for this 3-layered medium. What happens if we were to add one more layer below? You just have to very simply replace R23 with R23 tilde for 4-layered medium. So for 4-layered medium, you just take that, and then you can actually use this recursively to do this for n-layered medium very easily. Okay, you have n-layered medium. You know the Fresnel reflection coefficient at the bottommost layer. You can find the generalized reflection coefficient at this interface very easily using this formula, similar to that, not exactly the same as that. Okay. You know this R, you can find R tilde for the next one, then you can find R tilde for the next one, and then you can recursively work backwards and find R tilde for the very top one. So you can use this method to solve for reflection coefficient for any number of layers very easily. You can write the code very easily too. Yes?
So in this this formula for the wide electric field you have written here, are we considering how many reflection events are we considering in each layer?
We assume that there are multiple reflections in this layer, but no matter how many multiple reflections you have, there's only an outgoing wave and a downgoing wave. If you sum up all the downgoing wave, if you sum up all the outgoing wave, there are only 2 of them. In this region too, there's one downgoing wave, and there are many, many outgoing waves. And this is the sum of all outgoing waves. So there are actually multiple reflection events in here. Okay, and hence you can actually use this to model, say, if you have an arbitrary profile that you would like to seek reflection coefficient from, say, epsilon of z might look something very complicated. And you can actually model this with piecewise constant reflection coefficient, like doing a stepwise approximation. And then divide this into as many layers as you want, each layer being a constant, and then apply this formula to study for the reflection of this profile. This might be Z, this might be your Z. So this kind of method can be used to solve any arbitrary problem involving any number of layers. And once you know the solution in this layer, it's quite easy to find a solution in that layer by just transmission and applying the constraint condition over here. Okay, and then you can hence, if you know the solution in this uppermost region, you can easily work back down by using the constraint condition to find the complete solution in this region, and you can work downward and hence find all the solutions in every region if you want to. Okay. Are there any questions on this so far? Yes.
So what if the media is anisotropic?
Oh, anisotropic, this doesn't work. This is only for isotropic medium for each layer. If it's anisotropic, then things can get very nasty. Things can get very nasty. If the anisotropy is uniaxial, then you can still think of this as being the ability to decompose the wave into TE and TM type. But if the anisotropy is general, then you can have TE and TM wave coupling in this medium. Remember, before we got to this place, we decomposed the waves into TE type and TM type region. This is still true for lamination. That is, if you have a very thinly layered medium, lamination, then you tend to have epsilon in a tensor, and then you might have something like this, epsilon YY 0, 0, 0, epsilon Z, Z. And because of the lamination, epsilon XX and epsilon YY might be a constant equal to each other. This is called uniaxial medium. Only epsilon Z is different because the current will flow, at least the displacement current or the conduction current will flow the same manner in the horizontal direction, but will flow differently in the vertical direction, hence giving rise to uniaxial medium. This is called uniaxial. However, if this is general, if lamination is not like this, and if it's general anisotropy, then you cannot decompose the wave into TE and TM independently. You have to solve them as a coupled wave. As it propagates with this medium, and the solution will be a lot more complicated than this. But this model can be used to model lamination. Okay, you just divide the medium into thin layers. You find that they will have different conductivities and different things. Are there any other questions? There's a good question. Are there any other questions regarding this? Well, so the wonderful thing about this reflection coefficient is that it can have poles. And you saw that in the Fresnel reflection coefficient for the TM polarization, you could have poles. And I asked a question in the homework as to what poles mean. Okay, this one you definitely can have poles. This reflection coefficient will have poles when this goes to 0. What does that mean when the reflection coefficient has a pole? Does anybody want to offer an answer? It will have a pole when this vanishes. Okay, what does that mean? Yes? Resonator, very good. It's some kind of resonance. But since this is not a closed structure, what would that correspond to? It's an open structure. The wave can still propagate to infinity in the horizontal direction.
Extremely large reflected electric field.
Extremely large reflected field. That's also a correct statement. When you are at the pole location, the reflection coefficient goes to infinity. And what does that mean? It means that this reflection coefficient is extremely large. What does that mean to you? What is the physical meaning of that?
It acts like a half space.
What?
It's similar to a half space.
Yeah, I in the homework asked you to explain a half space case. What happens? What is the physical meaning of a pole when you have reflection coefficient of half space case? This is the general layered medium case. What is the meaning of a pole? The physical meaning of a pole here.
The wave propagating on the surface.
Yes, you're also correct about that. It means that you are in a situation where the reflection coefficient is infinite, which means that you don't need to send in any wave. You will get a reflected wave. That's what it means. The reflected wave exists without having to have an incident wave. So what does that mean? That means that you are in a situation where a wave exists in a layered medium without having an incident wave. You have a layered medium, a wave already exists there. A reflected wave exists there without having to have an incident wave. So what does that mean? That means that there's a guided mode on this function. Okay, a guided mode. Right? A guided mode is the only situation where you don't need an incident wave, and yet the reflected wave exists. So if you have a guided mode, one scenario is that you have wave propagating in here, so that you have maybe a standing wave, and then you have evanescent wave also. In this scenario, there's a reflected wave, but there's no incident wave. Okay, so a pole exists when there is a guided mode on this layered medium. There's the physical meaning of those poles. And the same meaning goes for your homework. What is the meaning of that when you have a pole in the Fresnel reflection coefficient for the surface plasma? Okay, but let's do something. I can write down this by inspection without having to memorize anything, and there's a good physical reason for that. Okay, because that expression has very nice physical meaning. So you can see the physics of this expression very clearly when you expand the denominator using the fact that 1 over 1 minus x is 1 plus x squared plus x cubed and so on. You use this power series expansion. And you do likewise to this denominator, you find that the generalized reflection coefficient is the Fresnel reflection coefficient plus the first term. The first term comes from this, which is T1 to R2 to E2 e to the 2. Let me just not write that in full. It just refers to this thing over here. And then the second term must come from that. Okay. The next term must be something like T1, 2, R2, 3, and this term multiplied by this term over here. Okay, let me just write that as R2, 3 squared, R2, 1, T2, 1, e to the 4. This is 2i, this is 4i, dot, 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 because it will be the 2 coming from here added to the 2 coming from here. And then you can add the next term will be this term times the third term, which is T1, 2, R2, 3 cubed, R2, 1 squared, T2, 1 e to the 6i, dot, dot, dot. And then you can keep writing. It will be something like this. You can see the pattern. Eight I, and what is emerging actually is something very physical. That's why I can write that expression down without having to memorize how it looks like. Because each term has a physical meaning. And if you look at the first term, what it means is that the ray comes in, the wave comes in. The first term just represents the reflection of the first interface. Okay, R1, 2 is what the first term is. This wave comes in as 1. The second term means that the wave goes into a 1-2 transmission. This is 1, 2, 3. It transmits 1, 2 into this medium. And then it gets reflected R2, 3. This is T1, 2. And then it gets reflected as R2, 3 over here. Okay. And then it gets transmitted as T2, 1 over here. Okay, so that's a wave that goes through a 3, 1, 2 transmission, R2, 3 reflection, 3, 1, T2, 1 transmission, and then the wave will gain a phase of transversing this layered medium. That's what this phase means. So finally, when it comes up as this term over here. Okay, here you have a question.
That's true. If we have like a 4-layer medium, and if the the generalized R2, 3 reflection coefficient have a pole, can you still do this expansion because that relies on x being less than 1?
Let's assume that there's a pole. It doesn't even have to be a generalized reflection coefficient. Let's assume that this is a plasma interface.
Okay.
And this will have a pole. Okay? But it turns out that we will never hit the pole with a propagating wave. I'm assuming a propagating wave in this region, and that in order to hit the pole for the surface plasma on a guided mode, you need evanescent wave. The wave profile looks something like this. So in order to excite this pole, you cannot excite this with a propagating wave. It will never hit the pole. And hence, the reflection coefficient will never be larger than 1. You can only hit the pole with the evanescent wave. Send in the evanescent wave, you get the reflected evanescent wave that is larger than 1. That's what the pole means. All these poles correspond to guided waves. They will have evanescent waves above the Lie medium. And you will never be able to encounter those poles. Okay? So I think you're correct. It's a very good observation. This expansion is only valid for magnitude of x less than 1. Equal 1 is not entirely kosher, but less than 1 you're sure that this convergence exists. Okay? So you can actually use this expansion when this reflection, this phototron has magnitude less than 1, which is true most of the time if you don't encounter a pole. Okay? So this is a story. Okay, any other questions regarding this expansion?
Could you just explain this third term? Like how
This term?
Yeah.
Okay, this term is, as you can see, is T12 transmission, and then R23 goes to R23 2 times. This is R23 1 time, R23 2 times. It's like this ray that goes like that. Okay, will undergo 2 R23 reflection, and then 1 R21 reflection, because this is an R21 reflection over here. Okay, and then it goes through a T21 transmission again. That's what the third term is. And you can keep tracing this, and then you can figure out that fourth term also has the same physical meaning. So that expansion that we have derived using constraint condition can also be expanded into a ray series. And each term has the interpretation of a ray. And you could remember this ray series and just write down this expansion by inspection, not having to memorize it. It must consist of a Fresnel reflection coefficient, and then the first term must involve the first partial ray. It's just one transmission, one reflection, and one transmission. And then all the subsequent multiple reflections come from this denominator. Okay, you can easily memorize this expression, or easily keep it in your mind. You don't have to memorize it. Okay, just store it in your mind. Okay, and there are other parts of the textbook which I wouldn't do. For instance, if you have a general inhomogeneous profile, you can also write the solution in terms of a Riccati equation, which I wouldn't do for this lecture. You can read up about that also for general inhomogeneous profile. Okay, and then for a linear profile, if epsilon of z is something like a plus bz kind of thing, you can actually write the wave equation like if it's a TE case where you don't have things sandwiched in between here. And it turns out that this equation can be solved in closed form. If epsilon of z is something of this form, you can convert this to something called an Airy equation. And then you can arrive at special function for this, called an Airy function. Airy function. Okay? And then you can write down the solution in terms of the Airy and the Berry functions, which is called the AI x and the BI x function, which are special functions that you can look up in handbooks. But a very good handbook for special functions is called it's a book by Abramowitz and Steger. Okay, everybody should have a copy of this book. And then there's another book by Russian, which is also very good, Crash Time and Reich. I'm not sure if I spell the Russian name correctly. Something like that. Okay. Crash Time and Reich. This is Russian. This is American. Okay, both of them are very good handbooks for special functions. And this has also many formulas for integrals that you should have.
2,000 pages, like, over 7.
Both of them are very thick books. Okay, very thick. You shouldn't carry them around with you anymore. You should put them in a USB stick and then just carry them with you. They are all available on the internet, I suppose. So I won't go into this special function thing and let you read them up by yourself. Okay. But what happens is that what interesting thing is that if you have an epsilon z that looks something like this as a function of z. Okay. So what happens is that the medium is becoming optically less and less dense as you move to the left-hand side. It becomes optically more and more dense. And we learned from undergraduate theory that if the light ray goes from an optically more dense medium to an optically less dense medium, what will eventually happen to the light ray? It will experience total internal reflection. So as the wave propagates this way into this medium, if I were to sketch a profile of this, it will slowly get refracted. Okay, because it is going from an optically more dense medium to an optically less dense medium. And finally, it will turn around. And that's how a light ray propagates. Of course, there will be some small reflections on the way, but in general, this is how the light ray propagates through this medium. And this one is called turning point. Okay, this point is, the turning point is where the light ray or the wave turns around. And then, how would the wave behave like in this region to the left of the turning point? Evanescent. Okay, so you have evanescent and you have propagating from this region. And if you trace the next ray over, the same thing will happen. The ray will turn around the same here. And then if you trace the next thing over, you do ray tracing, it will happen like that. And the place where rays become parallel to each other, this is called acoustic in ray theory. Okay, acoustic. Because that's where rays become parallel to each other. And this is where the ray picture breaks down. And every time when you have acoustic, the plane wave picture of a wave breaks down. So you can write things in terms of array functions to the left and to the right, and you can actually approximate them with plane wave, approximate them with evanescent wave to the left. But at this point, you cannot approximate them with anything other than special functions. That is the characteristic of acoustic. You need special functions. To approximate field nil acoustic. But I won't go into the detail of this, but you can read those things up. There are some interesting physics there. But other than what I say here, that should be sufficient for you to know. So, let's discuss how we solve for the solution of a source in a layered medium in general. So, we know how to propagate a wave, a plane wave, through a layered medium, irrespective of what angle the plane wave comes in. We know how to solve for the solution now. Okay, we just write down upward, downward wave in each region, match boundary condition or the constraint condition, and then obtain the solution in each region. So what happens if you have a point source? We have a point source. A point source does not produce a plane wave. A point source produces a spherical wave or a cylindrical wave. If it's a line source, it produces a cylindrical wave. We do not know how to bounce a spherical wave or a cylindrical wave of a flat surface. Okay? So we have to find a mathematical procedure to solve this problem. A simple way is to expand the field due to a line source or point source in terms of plane wave. And once we have done that, we will be able to propagate and bounce those plane waves of a late medium. So the next thing I like to do is to study the plane wave expansions of the field due to a line source or a point source. Okay, let's go with the line source first. So, which is the plane wave expansion of the line source field. So let's see how we do that, okay? We know how to solve for the solution of a line source. Before, if you have a line source, it's a source in 2 dimensions. So the solution should be a solution to this equation. Let's assume that partial z is 0 in a line source problem. Okay, that the line source can be represented by a delta function source. Okay, this is the field due to a line source. And in shorthand notation, we often would just write this as delta rho. Delta rho is